Alright, so talked about the conversions. So a couple things about heat. We just talked about the units that we can measure temperature in. And we've talked about this idea of thermal expansion and how to solve problems that relate to the temperature change, the type of substance it is, and what the original size is. So now we're getting into this relationship between heat and temperature. So definition of heat. Heat is the energy that flows from a higher temperature object to a lower temperature object because of the difference in temperatures. And so we have an SI unit for heat, which is joules. So the heat that flows from a hot to a cold originates in the internal energy of the hot substance, and it's not correct to say that a substance contains heat. So what ends up happening, as we said before, we look at this, so we say if we have a hot object, we have all these particles moving really, really fast. Alright, and then if we touch against a colder object and the particles really aren't moving that fast, the kinetic energy and the energy of movement of all those particles is going to cause bump into these particles, and so they're going to all end up bumping into each other until you get this transfer of heat so that they're all going to be moving at the same speed and ultimately have the same temperature. So, looking at this, we can look at the amount of heat that's supplied. So if we're transferring heat, what's going to be the result of transferring heat is we're going to end up with a temperature change. And we can quantify this with this relationship right here. So we can quantify that with the amount of heat that's needed to take a specific amount of matter, which is M, that has a specific heat capacity. So specific heat capacity is unique to every single material, and how much of a temperature rise that we're looking for. So this is the way that we relate heat to temperature. So keep in mind, specific heat capacity is interesting because every single substance is able to, in some cases, for all things being equal, like the same amount of substance, sometimes in order to raise the temperature of an object by 1 degree Celsius, it takes a lot more heat energy in joules to do that than it would be to do another different types of substance. So example of this is when you have a pizza in the oven, it gets hot, everything's the same temperature because it's been in the same oven for like half an hour, 350 degrees, you put it out on the table, it's cooling off at the same rate, and you go and 5 minutes later you touch the crust is cool enough, you think, okay, it's okay to eat, and you take a big bite of it, and then you bite into the cheese and the sauce and you burn your mouth. And the reason for that is that those different materials, the bread and the cheese and the sauces, all have different specific heat capacities, which means it's the amount of heat that they can hold, or what amount of heat in joules it takes in order to lower the temperature or raise the temperature by 1 degree centigrade. So again, we have a table, and these are again constants, so these are specific to all these materials, they never change, so they're the same. Just keep in mind this one right here, the human body, because we're going to use that a little later. It's kind of an odd thing to have as a specific heat of a human body, but it's there, and we use it for one of our questions in the future. Alright, so let's put this into application to a real problem. So as we said before, in this particular we have an object. Our object is a human being. It's a jogger that has a certain amount of mass right here, and they are generating this amount of heat. And typically what happens with humans that are jogging, there's thermal regulation, which means that the body's getting rid of that heat, but in this case we're assuming that there is nothing there. There's no heat being removed. So we're going to say if this person was to generate this amount of heat and they had this mass, what would be their overall increase in their temperature above what they usually are? So we go back to this equation that relates the heat to the amount of mass you have to this whatever substance is by the temperature change. And in this particular case, we know mass, we know the heat, we know, because this is a reference table, that there's the specific heat capacity of the human body is 3,500 joules per kilogram per degree centigrade. So we have that information referenced. So we have to rearrange this equation so that it's isolated for T, so we can figure what that temperature would be if we added this amount of heat to this size of matter to this type of matter. And by punching through the calculation, we see that their increase in temperature would be 3.5 degrees Celsius. Alright, so another example of this is this conservation of heat. So we have a calometer, which is basically a very insulated object, which doesn't allow heat to transfer very easily from the inside to the outside, so you can get very accurate measurements on the amount of heat energy that's been released to inside that substance. So what we're ending up here as well, so there's a conservation of heat. We're assuming that there's no heat loss through the surface. So the calometer is made up of 15 kilograms of aluminum and 20 kilograms of water. And initially the water, they all have the same internal temperature of 18 degrees Celsius right here. So they all have internal temperature starting at 18. Let's see this, starting at 18, and these are the masses of the two objects, but also there's different types. So we got water, aluminum, so we're going to have to reference two different types of specific heats. And then what's happening here is we have another mass that's being dropped in of an unknown material. So if it's an unknown material, we don't know what the specific heat capacity is because we always reference the material by what its specific heat is. So from this, we also know that it's going into it's coming in at an internal temperature of 97 degrees centigrade. So we can work this out, and so what we know is the temperature increase of the water and the aluminum, because it's at 18, it's going to increase because the final temperature of everything altogether is going to be 22 degrees centigrade. So when all these things, when all the heat is transferred from the hotter to the cooler, it's going to come to an equilibrium of 22 degrees centigrade. All right, so what we can do is start to map out this equation. So the amount of heat that's gained by the aluminum and the amount of heat that's gained by the water is going to equal the amount of heat that's been lost by that unknown particle right there, that's been added to the system. So that's how we relate this to each other. So what ends up happening is we can take all these things, we know all this information, we know the amount of the unknown substance, we know the temperature difference of the unknown substance because we're going from 97 to 22, so we have temperature difference there. The temperature difference right here for the water and the aluminum, they're starting at 18 and going to 22. So again, it's a little different, but again, the amounts we have of each are all there, and the specific heats are something that we'd reference from elsewhere. So we can rearrange this equation so that we can get everything on one side, but the only thing that we're trying to solve for is now the specific heat of the unknown material. And so if we plug in all our information and calculate all those values that have been given in the question, we calculate all those values, then we will get that specific heat. And then by understanding what the specific heat is, we should be able to then reference this in a book and actually figure out what kind of substance it is. All right.